Today we'll discuss ISI's UGB 2018 paper. Now the first question is, it says find all pairs x and y with x, y real satisfying the equation sin x plus y upon 2 equals 0 and mod x plus mod y equals 1. So for this first equation, we know that sin theta is 0 and theta is n pi. So from here we can write x plus y upon 2 must be equal to n pi, where n belongs to z, or we can say x plus y equals 2n pi. Now this second equation, it represents a square. So what we'll do is, we'll draw these two graphs and then we'll look for point of intersections which represent solution to this system of equation. So we know that this mod x plus mod y equals 1, it represents a square. So this point is 1, 0, it is minus 1, 0, 0, 1 and 0, minus 1. So this is the graph of mod x plus mod y equals 1. We have already discussed graph and its transformation in previous videos. I'll provide the link to the transformation of graphs in the description below. Now we'll draw these set of lines, which is x plus y equals 2n pi. So we'll take n as 0, we'll get x plus y equals 0. If we'll take n as 1, we'll get x plus y equals 2 pi. And if we'll take it as minus 1, we'll get minus 2 pi. And then we'll keep getting these parallel lines, which is x plus y equals 2n pi. So this is x plus y equals 0. And then x plus y equals 2 pi. So we'll intersect x-axis and y-axis at some 2 pi. And then at minus 2 pi also. So these two graphs, they'll intersect only at these 2 points. Now at these 2 points, we know that x plus y is 0. So we'll put x as minus y, then we can write 2 times mod of y equals 1, and then we'll get mod y as 1 by 2. So that is value of y is plus or minus 1 by 2. Now x is minus y. So if y is plus minus 1 by 2, x is minus plus 1 by 2. So we have two solutions, and one of the solution is minus 1 by 2 comma plus 1 by 2, and the other solution is 1 by 2 comma minus 1 by 2. Now question number 2 says, suppose that PQ and RS are two chords of a circle intersecting at a point O. It is given that PO is 3 cm, SO is 4 cm, and the area of triangle POR is 7 cm square. We need to find area of triangle QOS. So what we'll do is, we'll draw this figure. Now suppose this is our circle. And then we have chords PQ and RS. So say this is PQ and this is RS, and their point of intersection is O. It is given that PO is 3 and SO is 4, and we are also given that area of this triangle POR is 7 cm square. So this triangle. So area of this triangle is 7 cm square. We need to find area of triangle QOS. So let this be A1 and let it be A2. Now we can say that this triangle POR is similar to triangle SOQ. Angle in the same segment, they're same. So this angle P is same as angle S, angle R is same as angle Q. So these two triangles, they are similar. So if these two triangles, they are similar, then in that case we can write OP upon OS must be equal to OR upon OQ. Now OP is given as 3 and OS is given as 4. So from here we can say OR upon OQ is 3 by 4. Now say this angle is theta. So we can write A1 as 1 by 2 OR into OP sin theta, and A2 as 1 by 2 OQ into OS into sine theta. Now we'll divide them. If we'll divide them, we'll write a1 upon a2 as OR upon OQ into OP upon OS. Now OR upon OQ is 3 by 4. So this is 3 by 4, and then OP again is 3 and OS again is 4. So it is 9 by 16. The value of A1 is 7. So we'll put A1 as 7. That means 7 upon A2 is 9 by 16. So area of this triangle OQ is 7 into 16 divided by 9, which is 112 divided by 9 centimeter square. Now question number 3 says, let f be a function defined on R to R, and it is a continuous function such that for all x belongs to R and for all t greater than equal to 0, we are given that f of x is equal to f of e to the power t into x. Now what we'll do is, since this function is defined for all x belongs to R and it is a continuous function, so we'll replace x with x upon e to the power t. Then we can write f x upon e to the power t is equal to fx. Or we can simply write this as fx equals, and this is f e to the power minus t into x. Now it should be true for all the values of x and all the values of t greater than or equal to 0. It will also be true when t approaches infinite. So what we'll do is, we'll take this limit, which is limit t tends to infinite. Now this function f is continuous, so we can take this limit inside. So we'll take this limit inside, then we can write f, and it will be limit t tends to infinite, e to the power minus t into x. Now e to the power minus infinite is simply 0. So that means fx is equal to f0. So for any value of x, fx is always equal to its value at 0. That means this fx is a constant function. Question number 4, it is very simple question. It says there is a function f defined from 0 to infinite to r, and it's a continuous function such that f to x is equal to fx. It says show that the function g defined by this equation gx equals integral from x to 2x ft dt upon t for t greater than 0 is a constant function. So if it is a constant function, then its derivative must be 0. So what we'll do is, we'll differentiate this function. So we'll write g dash x, and since it is an integral function, we'll use Newton-Leibniz formula. So in place of t, we'll write upper limit. So it'll be f 2x upon 2x into derivative of upper limit, which is 2, minus lower limit. So it'll be fx upon x and then derivative of lower limit. So we can write g dash x as f2x, here 2 will cancel, minus fx upon x. Now f2x is same as fx, so that means g dash x is 0 for all x greater than 0. It simply means this function is a constant function. Now question number 5, it says let f be a differentiable function such that its derivative f dash is a continuous function and mod of f dash x is always less than equal to 1 by 2. Then it says define a sequence of real numbers an such that a1 is 1 and an plus 1 is equal to fan for all n belongs to n. Now we need to prove that there exists a positive number m such that for all n belongs to natural numbers, mod of an is always less than or equal to m. Now since in this question the given function is a differentiable function, so what we'll do is we'll apply Lagrange's mean value theorem for this function in the interval say x comma y. So we'll use Lagrange's theorem, then we can say there exists some c in this open interval x comma y such that f dash c is equal to fx minus fy upon x minus y, and if we'll take a mod sign, then we can simply write this as mod of fx minus fy upon x minus y, and it is equal to mod of f dash c. Now in the question it says any derivative, its modulus will always be less than equal to 1 by 2. So we can write this as this is always less than or equal to 1 by 2. So from here we'll get this condition, which is mod of fx minus fy is less than or equal to 1 by 2 into mod of x minus y. Now we'll take x as an, y as an minus 1, then we can write this as mod of f an minus f an minus 1 is less than equal to 1 by 2 an minus an minus 1. Now fan is an plus 1, so we can write this as an plus 1 minus an, and it will always be less than equal to 1 by 2 an minus an minus 1. Now in the same way we can write an minus 1 will be less than 1 by 2 into an minus 1 an minus 2. So it will be 1 upon 2 square an minus 1 minus an minus 2. And if we'll continue like this, then we can say that mod of an plus 1 minus an will always be less than or equal to 1 upon 2 to the power of n minus 1, and eventually we'll get mod of a2 minus a1. So now we'll be using this result to prove this mod of an is less than equal to some number m. So what we'll do is we'll write mod of an plus 1 minus a1. Now we can write mod of an plus 1 minus a1 as mod of an plus 1 minus an, and then plus an minus 1, and then plus it'll continue up to a2 minus a1. Now we know that mod of x plus y is always less than or equal to mod x plus mod y. So we can write mod of an plus 1 minus a1 will always be less than or equal to mod of an plus 1 minus an plus mod of an minus 1, and continue up to mod of a2 minus a1. So we can write this as mod of an plus 1 minus a1 is always less than mod of an plus 1 minus an, which is less than or equal to 1 upon 2 to the power n minus 1 into a2 minus a1. So it is less than equal to 1 upon 2 to the power of n minus 1 a2 minus a1. In the same way, it will be less than 1 upon 2 to the power of n minus 2 mod of a2 minus a1. Eventually we'll have just a2 minus a1. So we'll take mod of a2 minus a1 common. So we'll write mod of minus a1 is less than equal to, and this is mod of a2 minus a1, and then it'll be this gp, which is 1 plus 1 by 2 plus 1 upon 2 square up to 1 upon 2 to the power of n minus 1, and any partial sum is always less than or equal to sum of infinite series when the terms are positive. So it will always be less than 1 plus 1 by 2 plus 1 upon 2 square up to infinite. So we can write mod of an plus 1 minus a1 will always be less than or equal to mod of a2 minus a1, and this is a upon 1 minus r. So that means we can write mod of an plus 1 minus a1 is always less than or equal to 2 times mod of a2 minus a1. So for any value of n, we'll get this result, which is mod of an plus 1 minus a1 is always less than equal to 2 into mod of a2 minus a1. So if it is true for any value of n, then we can simply write mod of an minus a1 is less than 2 into a2 minus a1. Now we know that mod of x minus y is always greater than mod x minus mod y. So we can actually write this as mod of an minus mod of a1 is less than equal to an minus a1 mod, and which is less than 2 times mod of a2 minus a1. So from here we can say mod of an will always be less than or equal to 2 a2 minus a1 and then plus mod a1. Now in the question it is given that a1 is 1. So we can write mod of an is less than 2 times mod of a2 minus 1 and then plus 1. Now since this function is a differentiable function and its f dash is also a continuous function, it means this a2 will be a finite value. So this an will always be less than or equal to 2 mod a2 minus 1 plus 1, which is some finite real number m. Now question number 6, it says let a, b, c be 3 numbers such that a is greater than or equal to b, b is greater than or equal to c, and which is greater than 0 be real numbers such that for all n belongs to n, there exist triangles of side lengths a to the power n, b to the power n, and c to the power n. We'll need to prove that such triangles, they'll always be isosceles. We'll prove this result with contradiction. So let us say that let the triangle formed by a to the power n, b to the power n, and c to the power n not an isosceles triangle. So that means a is unequal to b, b is unequal to c, and c is unequal to a. Now if a to the power n, b to the power n, and c to the power n, they represent sides of a triangle, in that case they must satisfy triangle inequality, and which is sum of two sides must be greater than third side. So from here we'll say b to the power n plus c to the power n must be greater than a to the power n. Now we'll divide it with a to the power n, then we can write b upon a to the power n plus c upon a to the power n, and it is greater than 1 for all n belongs to n. Now in the question it says a is greater than or equal to b and b is greater than or equal to c, and our assumption says that it is not an isosceles triangle, so that means they are not equal. So we can strictly write a is greater than b and b is greater than c. So in this case b upon a is less than 1 and c upon a is also less than 1. Now since it is true for all the values of n, it will also be true when n tends to infinite. So what we'll do is we'll take this limit n tends to infinite. Now since b upon a is less than 1, so this b upon a to the power infinite will be 0, and in the same way c upon a to the power infinite will also be 0. From here we'll get this result, which is 0 is greater than 1, which is impossible. So that means our supposition is wrong. So this triangle, it is an isosceles triangle. So we have proved this result using contradiction. Now question number 7, it says let a, b, c be 3 natural numbers such that a square plus b square equals c square and c minus b is equal to 1. So we need to prove that first a is odd. Now we can write a square as c square minus b square, which is a square, and this is c plus b into c minus b. Now c minus b, it is 1. So we can write a square as c plus b. Now c minus b is 1, so which is an odd number. So if c minus b is an odd number, that means one of c and b is even and other one is odd. So if we have one number even and other number odd, then the sum of even number and odd number is also an odd number. So a square is an odd number, and if a square is an odd integer, in that case a is also an odd integer. So that's your result number 1. Now in the second part, we need to prove that b is divisible by 4. So now we have two results. C minus b is equal to 1 and a square equals c plus b. Now what we'll do is we'll subtract this first from second. So it'll be minus 1 and it'll be minus c plus b. So we can write 2b, and this is a square minus 1. We'll write this b as a minus 1, a plus 1 upon 2. Now in the first part, we have already proved that this a is an odd number. So let us say a is some 2k plus 1. So we'll take a as some 2k plus 1. Then we can write this b as a minus 1, which will be 2k, and then a plus 1, which will be 2k plus 2 divided by 2. So now we can cancel this 2. We can write b as 2k into k plus 1. So b is a multiple of 2, and then it's a product of two consecutive integers, k and k plus 1. So out of these two, k and k plus 1, one of them must be an even number. From here we can say that b is divisible by 4. Now we'll come to its third part, and that is we'll need to prove that a to the power b plus b to the power a is divisible by c. So let us take a to the power b. Now we have already shown that this b is a multiple of 4. Then we can write this b as some 4m, and we can write it as a square to the power 2m. Now a square is c plus b and c minus b is 1. So we'll add them. Then we can write 2c equals a square plus 1, and we can write a square as 2c minus 1. So we'll write a square as 2c minus 1. Then we can write this as 2c minus 1 to the power 2m. Now we need to find divisibility by c, and the shortcut says express this a to the power b as some multiple of c, and then whatever is the constant term, that's your remainder. If a to the power b is divided by c, it leaves the remainder minus 1 to the power 2m, that is simply 1. Now we'll find b to the power a. Now we know that b is simply c minus 1, so it will be c minus 1 to the power a. Now again, if we'll use shortcut, we'll get this remainder as minus 1 to the power a. So if b to the power a is divided by c, then remainder will be minus 1 to the power a, and since a is an odd number, remainder is simply minus 1. Now we'll add a to the power b and b to the power a. Then this remainder is plus 1 and this remainder is minus 1, which will eventually cancel out. So that means a to the power b plus b to the power a is divisible by c. And this is how we solve these questions. Now question number 8, it says there is some matrix A which is n cross n matrix such that any element aij belongs to this set which is 1 and minus 1. So any entry in this matrix is either plus 1 or minus 1. Now it says that suppose that ak1 is 1 for all k between 1 and n both inclusive, and this summation k varies from 1 to n, aki, akj is equal to 0 for all I unequal to j, then show that n is a multiple of 4. Now we are given this matrix which is A, and that's an n cross n matrix. Now ak1 is 1 for all k between 1 and n. So that means a11 is 1, a21 is 1. So all these first element in this first column, they are 1. Now we are also given this condition that summation k varies from 1 to n, aki into akj equals to 0 for all I unequal to j. So what we'll do is, in this we'll take I as 1. So we'll take I as 1, then we can write this summation as k varies from 1 to n, ak1, akj, and this is 0 for all j unequal to 1. Now aki is always 1. So from here we can write summation k varies from 1 to n, akj is equal to 0. So that means in any column j, sum of all the elements must be 0. If sum of all elements must be 0, then it simply means half of them should be plus 1 and other half should be minus 1. And we know that there are altogether n elements. So say we have m ones and m minus ones. So we have total 2m elements in this jth column, and total number of elements in any column is simply n. So we can say that this n, it is at least an even number. So we have proved that this n is at least an even number. Now in this expression, if I'll put j as 1, then we get aki into AK1, AK1 is again 0. That means for any column I again it will have M plus 1s and M minus 1s. Now, if we look at this AKI into AKJ, it simply means for any given row, we are multiplying this element, that is the element in this ith column with the element in jth column, and then we keep multiplying them, and we'll add all such multiplied terms, then its sum will be 0. Now, when we'll multiply these two expressions in any given row, then we'll have four kind of products. So either it will have plus 1 into plus 1, or it will have plus 1 into minus 1, or minus 1 into minus 1, or minus 1 into plus 1. So we'll have these four kind of products. Now what we'll do is we'll say let there be R such products in this expression. So out of these M minus 1s, R minus 1s, they are multiplied with minus 1, and M minus R minus 1s are multiplied with plus 1s. So we have R such terms, and here we'll have M minus R such products. Now for the second product we have taken R minus 1, so that means for this one we'll have M minus R such products, and in the same way we'll have R such products. Now if we'll add all these products, then we'll have, now this is plus 1 into plus 1, so 1 into R. Now this is minus 1, so it'll be minus 1 into M minus R, and then again plus R, and here it'll be minus 1 into M minus R, and again it'll be simply 0. So if we'll simplify it, we'll get R minus M plus R minus M plus R equals to 0. So from here we'll get M equals 2R. Now N is 2M, so we'll replace M with 2R. We can write N equals some 4R, and from here we can say that this N, it is a multiple of 4, and that is the answer to this question.